This is the second section of chapter 3 on further centers of mass, and this section is about finding the center of mass of a uniform body. So what we mean by a uniform body is a three-dimensional shape where we have the outline of the shape here, a line or a curve, which we know the equation of, y equals f of x, that would be some sort of function of x. And this is rotated 360 degrees around the x-axis. So this ties in with volumes of revolution, which you would have learned in core maths. This does mean that the center of mass in the y direction, y bar, is going to be 0 by symmetry. So that's going to be right down the center there. And the density of this, or its mass per unit volume, is going to be represented by rho. Now, since we can use symmetry to find the center of the mass of the y direction, it does mean if I had a sphere centered on the origin, that the center of mass of the sphere is going to be at the very center of the sphere. And imagine that I had some sort of cylinder where like the center part of the cylinder was here. I had a cylinder going around there. So a line rotated 360 degrees around the axis. Actually, I might just draw that in and then take it out afterwards. So imagine this, and this is some sort of cylinder. Then the center of mass is going to be at the center of the cylinder here. So the way that we're going to work out what the center of mass is we're going to start by dividing this up into strips, or sorry, discs. And each one of these discs is going to have a width of delta x, and basically the radius of each one of these discs here is going to be y. And let's say that this disc is at a distance of x from the origin, so it's a distance there to the center of the disc. So one of these, what I'm going to call fundamental discs, will have a volume of pi times the radius squared, which is y, times by its thickness, which is delta x. Therefore then, the mass of this fundamental disc, this disc here, will be its volume times the density. So it's volume pi y squared delta x times by its density, which is represented by rho. So from there, we have the mass times the center of mass of one of these discs is rho pi y squared delta x times by x, because x is where the center of mass of that disc is. So we can use symmetry for that. And I'll just rewrite it as rho pi xy squared delta x. Now we actually want not just one disc, but we want lots and lots of discs, and we want to make the width of the disc delta x tend to 0. So if we take the limit as delta x tends to 0, then our sum of all of these discs becomes an integration, and it's going to be our little expression that we had up here, our mass times the center of mass of all of these discs divided by the mass of all of these discs. Now you'll notice that I've put the rho and the pi on this side. Over here on the left hand side they're constants, and they're still here in the formula, but we don't really need them. So it's useful actually just to have the formula in this form here. You can write the rho and the pi down, but they're always going to cancel out anyway in the types of questions we're going to be doing. Now if we instead have a shape where it's rotated around the y-axis instead of the x-axis, then this becomes our formula to find the center of mass in the y direction. It's basically the same as this, but we've just swapped the x's and y's around, and it will be x bar, which is 0 by symmetry, because we're going to be rotating around this way. Example 7, find the center of mass of the uniform right circular cone with radius r and height h. So we'll start by drawing that out. So here's a sketch of my right circular cone, radius r, height is h. So I can see that I'm going from 0 to h. they're going to be my limits. I've drawn on one of these little discs here, fundamental discs, so you can see I'm taking the width of the disc as delta x. To know the radius of this disc, I need to know its height, so I need to know the equation of this line here. So I know it's a straight line, it's going to be of the form y equals mx plus c. It passes through the origin, so c is 0. M is going to be the gradient of this line, which is going to be its rise over its run, so r over h. So that gives me the equation of like the boundary, the outline of this, and also what's going to give me the height of one of those discs, y equals r over h x. Now I can just plug that into the formula to give me the centre of mass in the x direction. And the limits, I know there are no limits on here, but the limits we need to put those in are going to be 0 and h. So I'm going to have the integral between 0 of h times by x times by y all squared. So that's going to be r over h x all squared dx all over integral 0 to h, and then r over h x, again all squared dx. So if I simplify that out, I'll have r squared over h squared, put it over here, it's a constant. I'll get x squared from here times by x cubed. Do the same at the bottom, r squared over h squared, constant over this side, leaving just x squared over here. Now you can see that these are going to cancel out. Now that just leaves me integrating these. So x cubed becomes x to the power 4 over 4 between my limits of 0 and h over, that'll be x cubed over 3, or a third x cubed, again between the limits of 0 and h. Then putting the h in, so I'll write it as a quarter h to the power 4, because it gets a bit messy, fractions over fractions. And then at the bottom it will just be a third h cubed. Obviously when you substitute in the 0, there's going to be nothing there, so we'll just simplify that, and that just becomes 3/4 h. Now this is a standard result which you can quote without proving it, but if you are asked to prove that the centre of mass is 3/4 of h, this is the method we need to use. Otherwise, just quote this result and use it. So just to finish it off, x bar is 3/4 h, y bar is 0, and we get that by symmetry. Example 8, find the centre of mass of the uniform solid hemisphere with radius r. So here's my diagram, hope it sort of makes sense. It's my hemisphere. Here's one of my little discs here of width delta x. Then we also need to know the equation which bounds this hemisphere. So it's just going to be a circle, isn't it? X squared plus y squared equals the radius squared, where the radius squared is a capital R. But since it's only half of a circle, we're only taking the values where x is positive. Otherwise we'd end up with this bit over this side. We don't want that. Now y can be positive or negative, but x must be positive, so I suppose we could put that x needs to be greater than or equal to 0. So just like we did before, we're going to start with our formula here. We need to know the equation in the form y or y squared, so that's going to be easy enough. We can just rearrange our formula and get y squared is equal to r squared minus x squared. So from there we will have x bar is equal to the integral between our limits, which are going to be 0 and r, 0 and capital R, and then it's going to be x times by y squared, so that's going to be r squared minus x squared, so we don't need to square anything, it's squared already, all over integral between 0 and r of y squared, and that is just r squared minus x squared dx. The next step is just to expand the brackets at the top. Next comes the integration. Next we'll put in our limits. Now I only really need to worry about putting the r in, because when I put 0 in, all of this is just going to become 0. So this is what we get once we've substituted in r. Now this simplifies quite nicely. A half r to the power 4 minus a quarter r to the power 4 is a quarter r to the power 4. And then r cubed minus a third r cubed is going to be 2/3 r cubed. So our last step is just to simplify that. And that leaves 3/8 r. Now, just like previously, you can quote this result in questions unless the question asks you to prove that the centre of mass is 3/8 r. And just like before, we can also say that y bar is 0 by symmetry, and our x bar is this 3/8 r, 3/8 of the distance from the origin. Example 9. Find the centre of mass of the uniform solid of revolution formed by rotating a finite region enclosed by the curve y equals x squared plus 1. The x-axis, analyse x equals 0 and x equals 3 through 360 degrees about the x-axis as shown in the diagram below. So start off by writing our formula down, and then we can say that y bar equals 0 by symmetry. So x bar is going to equal our integral between our limits, which are going to be 0 and 3. And then it's going to be x times by y squared. Now y is x squared plus 1, so it's going to be x squared plus 1 all squared dx, and that's going to be divided by integral between 0 and 3 of just x squared plus 1 all squared dx. So now what we'll do is expand the brackets. So if we square this, we'll end up with x to the power 4 plus 2x squared plus 1, and that needs to be times by x. So that's going to be x to the power 5 plus 2x cubed plus x. And then at the bottom, we don't need to times by x, so it'll just be x to the power 4 plus 2x squared plus 1. So now we can integrate. So I'll have 1/6 x to the power 6 plus x to the power 4 divided by 4, so 2/4, which is a half. So a half x to the power 4 plus a half x squared. Our limits are 0 and 3, and all of that divided by 1/5 x to the power 5 plus, so this will be 2/3 x cubed plus x, again between 0 and 3. So now we can plug in those limits. So this is what I get when I substitute in the 3. Obviously when I put the 0 in, it's just going to give me 0. So evaluating the top on my calculator, I get 3/2. And again with the bottom on my calculator, I get 3/8/5. Now we'll divide those by each other, see what we get. And that gives me 555/232. So that's my value of x bar, and I've already said previously that my centre of mass in the y direction is 0. So we could, as we've done with the others, or we haven't done with the others, we could write the answer as a coordinate, but writing it this way is fine. Example 10. Find the centre of mass of the uniform hemispherical shell, it's almost like a tongue twister, with radius r. So what we need to do in this question is like imagine a hemisphere in which we remove a slightly smaller, that's meant to be small in there, a slightly smaller hemisphere leaving a thin shell. So imagine this hemisphere here is just slightly smaller than this one, and it gets scooped out, and then what we're left is this shell. Okay, it's probably not going to look much different in my diagram, but imagine like an eggshell or a ball or something, and we know that the radius of this hemisphere is r. This slightly smaller one inside we're going to call little r. So you could imagine that the thickness of this shell, is going to be r minus r, big R minus small r. And what we want to do is imagine what happens as r tends to r. So what happens, or what we're going to work out, is what happens when little r tends to big R. So this little radius here is going to get closer and closer to R, leaving this really thin shell. So the way that we're going to do this is treat it like a composite shape, but with one shape with another shape removed. So here we're going to have this larger hemisphere with radius R. So hemisphere with radius R, big R, and then we're going to subtract from that the hemisphere with radius little r, radius little r. Okay, you can use any letter you like, but just using big R and little r makes sense to me. Now the volume of a sphere is 4/3 pi r cubed. So if we times that by rho, we get the mass of a sphere. So if we divide that by 2, we're going to get the mass of a hemisphere, and that's going to be 2/3 rho pi r cubed. And I'll just correct that r should be big R, because when we come to the smaller one, it's going to be exactly the same thing, but 2/3 rho pi little r cubed. Now we can use the standard result for the center of mass of a hemisphere. We proved that previously. So in the x direction, that would be 3/8 of its radius, which is r, and y bar is going to be 0 by symmetry, and then x bar is going to be 3/8 little r, and again y bar is going to be 0 by symmetry. Okay, so now for the center of mass x bar, we're going to do the mass times the center of mass of the outer hemisphere minus the mass times the center of mass of the inner hemisphere divided by the masses subtracted. So I've just factorized this, so the mass of the outer shell minus the mass of the inner shell, or the inner hemisphere. Now we can cancel out the 2/3, and we can cancel out rho pi from all of the terms. So then the whole expression then will simplify to 3/8 big R to the power 4 minus R to the power 4 over R cubed minus little r cubed. So once we've got that expression written down, once we've cancelled down, the next thing to do is now to factorize it. Now the top is, we can use the difference of two squares, and actually we can use the difference of two squares again here. Actually, let's write this down so it saves some working. So this here is going to become big R minus R times by big R plus R. And then for the bottom, it's a useful result to be able to know what we get when we factorize the difference of two cubes. And this is the result down here, big R minus R, and in this quadratic here. Now what's going to happen is when I factorize this again using the difference of two squares, that means that this R minus R is going to cancel out with this R minus R. So that will give us this simplified expression here. We can't simplify this anymore. But at this point, we want to see what happens as little r tends to r. And that's what we said right at the beginning here. So if we do that, at the top, we will have 3/8 times by this little r is tending to r. So r plus r, we will have 2r. And then as this tends to big R, that becomes big R squared. So we're left with 2 lots of big R squared all over. So we'll have R squared plus another R squared plus a third R squared. So we'll simplify this. Now I wrote a plus here. I meant times because obviously this is times in together. So we'll simplify this and see what we get. So we'll have 3 over 2 r cubed. We've got 3 over 8 times by 2 times by 2 again. R times by r squared r cubed. And then we've got 3 lots of r squared. We can simplify that. And that just becomes half r. Not 1 over r, but half r. So again, this is one of these results which we can quote or prove if we're asked to prove it from scratch. But if you're not asked to prove it, then you can just use this result that the center of mass of a uniform hemispherical shell is going to be half the radius of the outer shell. Example 11. Show that the center of mass of the uniform hollow right circular cone with radius r and height h is at a distance 1/3 h from the base along the axis of symmetry. So here's a diagram representing what's going on. Now, unfortunately, we can't use the method we used before for the shell, where we do the volume of the outer one minus the inner one. The method for this is that we need to actually divide the surface of the cone up into these triangles. Now, if we look at one of these triangles in more detail, they're all of height h, and the vertex pointed end here of this triangle is going to be at the origin here. Just put O. And the center of mass of a triangle we know is 2/3 of the length of this line from the vertex end. So center of mass here is 2/3 h along here. Now that's going to be the same for all of the triangles around this cone. So imagine around this cone, all of these centers of mass are going to be at a distance of 2/3 h. So the center of mass of each triangle is 2/3 h from the vertex end of the cone. In other words, the center of mass of the whole cone is 2/3 h from the vertex end of the cone. So that means that the center of mass is 1/3 h measured from the base of the cone, because that's what we were actually asked to show. So we've shown that by dividing up into these triangles using the center of mass of one of these triangles, the center of mass of all of the triangles around the cones is going to be this 2/3 h from the vertex end, which means it's going to be 1/3 h from the base of the cone. Example 12. Find the position of the center of mass of the frustum of a right circular uniform cone of end radio 1 centimeter and 4 centimeter and height 7 centimeters. Okay, now you might look at this diagram and think, hang on, that's not a frustum. But the easiest way to do this question is to move where the top of the cone would be, the vertex of the cone would be, move that to the origin, so that actually this is the frustum here. And then it's much easier then to work out the center of mass in relation to this point here, you'll see in a moment. Now we know that the frustum is going to be a larger cone, this cone here. Take away the smaller cone at the top. What we're missing is the height of the large cone. We can use similar triangles to help us work that out. the frustum base has a radius of 4 and its top has a radius of 1, which means that the larger cone has a radius of 4 and the smaller one has a radius of 1. So there's a ratio of 4 to 1 here. Now we know that the height of the frustum is 7. And let's call the height of the large cone h. See if we can work out what h is. Now for the small cone, using scale factors, then the height of the smaller cone must be a quarter h, or h over 4. So that means in terms of h, the height of the frustum is a h minus a quarter h. And that is equal to 7, the height of the frustum. So 3/4 h is equal to 7 times both sides by 4 over 3, and we've got h is equal to 28 over 3. Now we're going to use this table to work out the centre of mass of the frustum. So we need the mass and the centre of mass of each part of this like composite shape. We're going to be subtracting, aren't we? So first of all, starting with the large cone, we've got its height and its radius. And for the small cone, its height is given as a quarter h, which is 7 over 3 and a radius of 1. Now if we want to find the mass is going to be rho times by 1/3 pi r square h. So we'll just substitute those values in. And if we then work out what that gives us 448 over 9 rho pi. We'll do the same for the small cone, and that gives us 7 over 9 rho pi. So now we're going to work out the centre of mass of each of these two cones here, starting with the larger cone. I'm going to give the centre of mass relative to the origin, so this vertex end here, and we know from a previous result that the centre of mass of a cone is 3/4 h from the vertex end. So for the large cone, its distance is going to be 3/4 away, or from the vertex end, of its total height, and that height is h, which is 28 over 3. So 3/4 times by 28 over 3, which is 7. So I could write its centre of mass as 7, 0, because I know that the centre of mass in the y direction is going to be 0 because this is symmetrical. And then for the smaller cone, its centre of mass given from this distance from the vertex end. Now this is the advantage of putting the vertex here. If we drew it so it was something like this, and we had the top of the frustum or the smaller end of the frustum here, it's going to be tricky trying to write the centre of mass in terms of maybe the base of the frustum. We have to sort of fiddle with some numbers, and the reason we can move the shape around and still get a correct answer is because we're given an answer relative to some part of the frustum, so relative to the base or the top of the frustum. So it doesn't really matter where we place the cone on the axis, so it makes things easy for ourselves and put the vertex there. So yeah, 3/4 of the height, so 3/4 times by 7 over 3, and that gives an x centre of mass as 7 over 4, 0. So now the centre of mass of the whole thing, so the mass times the centre of mass of each part, so 448 over 9 rho pi times by its centre of mass, and then we need to subtract the smaller cone, so that's 7 over 9 rho pi times by 7 over 4, and then we divide that by the difference between the masses since basically the small cone's been taken off. So that's going to be 448 over 9 rho pi minus 7 over 9 rho pi. Now the pi's and the rho's all cancel out, then if I calculate the top and the bottom, I get 4165 over 12 divided by 49, and that simplifies to 85 over 12. Now, that's probably not a useful answer because that's the distance from my origin. Since it's a frustum, I probably want the distance from the base, and to find the distance of the center of mass of the base, I want to take its total height and then subtract where the center of mass is. So that's going to be 28 over 3 minus 85 over 12. Doing that calculation gives you 9 over 4. So we can say that the center of mass x bar is 9 over 12 from the base of the frustum, So on questions like these, it's often useful to move the shape around to make your working easier, to suit yourself. So here, putting the vertex here just simplified some of the calculations of it. So you should now be able to do exercise 3B on pages 95 to 98.